So suppose you are given a problem like this, where you have our reactants in red with our arrow with some question mark above it that is going to be producing our products in green. And so we're asked to find out what this question mark is. So how did we get this to happen? So over here on the left we have a carbonyl group that is going to be turned into an alkene. At the same time we are adding what looks like two carbons to our reactant to make our product. And so we're asked, how do we do this? Well, we can go ahead and introduce a new type of reaction called the Wittig reaction, which will do this the fastest and most easiest way for this particular example. So, what is the Wittig and how do we make it? Um, First, tackling how we can make it, um, let's address, first of all, what are we attaching? Well, it's two carbons, and so we're going to do this like this. So we have our two carbons right here, so carbon 1 and carbon 2, and those will make up these carbons over here. Right? So great, those are our two carbons, and now we have to do the Wittig part of it. And so we're going to throw it in a pot with a bunch of some triphenylphosphine. And as our first step, what we expect to happen is the lone pair of electrons on this phosphorus will go and attack the alkyl halide. Let me do this in a different color actually. So the lone pair on the phosphorus will attack the alkyl halide, letting this bromine leave with a lone pair that was shared between the carbon and the bromine. So now let's draw what we're left with. Still our two carbon group that's now attached to a phosphorus and a pH right here, pH right there, and a pH right here. And that's our triphenylphosphine. So great, we're getting closer. Now the next step is to now combine it with some sort of a strong base. And what you'll usually see being used in textbooks is going to be butyl lithium, so we'll use that here. And so here's our strong base. And we need to identify a proton that's going to pull off, and the most accessible one is going to be this one right here. Oops, and I forgot one little thing. There should be a positive charge right there. So going on with our mechanism, we see an acidic proton right here on this carbon, and so our strong base goes over, pulls it off, and the lone pair of electrons will flop onto this carbon right here. Our next product that we're going to make is down here, and we can go ahead and call this species an ylid. And that's being kind of generic. If you want to be a little bit more specific, it's called a phosphonium ylid. So I can write that right next to it. Let's do it right here. Phosphonium ylid. And so what is just a generic ylid? Well, this might be the first time it's introduced in organic chemistry, but it's simply just two opposing charges, so a negative and a positive, that are right adjacent to each other. And the reason for, well, first of all, you might be expecting that, well, why don't these electrons on the carbon come down, make a double bond with the carbon phosphorus, and the really generic or basic understanding of this is, well, looking at each atom's octet, are those rules obeyed? So our phosphorus has 4 bonds to it and a positive charge, and so we expect there to be 8 electrons around it, which obeys the octet rule. And then our carbon has 1 hydrogen, which I can draw in. It's a little bit, there we go. It has one hydrogen bond, it has a bond to carbon and then a bond to phosphorus as well as a lone pair. And so that would also follow its octet rule. And so we don't see, and just for the really simple explanation, we don't see this happening at all. I'll kind of shade that out. So this would be how you'd make your Wittig reagent. And let me just say this is the Wittig reagent. Great, so now how is it used? So once we've made our Wittig, we are going to throw into the same pot as our carbonyl group. So in this case we have our aldehyde. And so now we just have to provide a mechanism and then we can solve the problem. So uh, starting with the things that have the highest energy, we're going to do something with them. And that in that case, that's our carbon anion. So the carbon anion sees a partially positive carbonyl group, and so we can see the electrons will attack that carbonyl, throw the extra electrons up to the oxygen, and so now we've made our intermediate. Oops, I missed that one. There we go. And right here. Great, and so this is our intermediate, and we actually do have a word for this one. It is called a betaine, or a betaine. Spell that for you. Betaine. And definition for this is just two opposing charges, like the ylid, but they're separated by two atoms. So in this case, we have two carbon groups separating an O minus and a P plus. So from here, next step in the mechanism, again following the highest energy thing, the extra electrons on the oxygen are going to want to create a bond with our phosphorus, but the second it does that, this bond, this carbon-phosphorus bond, is going to want to break in order to obey that octet rule. And so when we see that happen, those electrons will flop down. And so now when those electrons flop down, again obeying the octet rule, we can't have this oxygen bonded to carbon anymore, so we see electrons get flopped onto the oxygen, leaving us with our final product. So great. And so in regards to cis and trans, again, simple explanation is that in the most cases, the cis alkene will usually be made, but for a greater understanding of why, I will go over that in a separate video. But this would be the entire mechanism of how you would make your Wittig reagent and then how you would use it in some sort of synthetic step.